Hi guys, today we're going to be learning how we can solve this Lambert W function equation. Oh, it looks kind of hard and tricky, but it's actually very simple. At least if we have a basic knowledge of how Lambert W function works. So how can we solve this equation here? Actually very simple. Now, first of all, we have to understand the definition of Lambert omega function. Now don't forget that by definition, we know that when we have Lambert function of z, for example, let's say equals y, right? Now to get rid of this w function, we'll say that z will be equals to y e raised to power what? Y. This is by definition of Lambert omega function, right? Just like by definition of sine function. Let's say you have something like sine theta equals, let's say, 5 for an example. Now to get rid of this sine as a function, you take the arc sine of this side, right? So then theta, no more sine, will now be arc sine 5. So that's just the same idea here also. So this w function is just similar to this sine function. That is, to get rid of this w function, right, we are going to take the exponent of this variable here. That will be y e to the power of y. That's by definition, okay? It's not hard. So in our case here now, our z is this exponent here, right? Then y is x to the power of x. So now we can get rid of this w function following this idea. So that means this here now will now give us e to the power of a squared plus 1 plus x to the power of x will now be equals to x to the power of x e to the power of x to the power of what? X, right? We have gotten rid of this w function by this definition. So now what's the next thing to do? Now to make this thing simpler, right, let us make use of substitution. So let x to the power of x equals y, right? We don't like this x to the power of x, it looks scary. So we can rewrite this as e to the power of e squared plus 1 plus y, that's equals to y e to the power of what? Y. Now this one is kind of easier. So we have gotten rid of the w function here now. So the next thing to do here is now simplification, normal exponential simplification, right? Using law of indices and all that. So to simplify this now, the smart thing to do is, don't forget, anytime you have the same base, right, let's try to bring them together, right? That's normal idea of exponent. So divide both sides by e to the power of y. So we have e to the power of y because they have the same base, e to the power of y. So e to the power of y cancels e to the power of y. Now, don't forget here from the law of indices that says that when you have, let's say, a to the power of m all over a to the power of n, right, to give us a to the power of m minus n. We use that same idea here, e. So we're going to subtract. So here we have e to the power of a squared plus 1 plus y minus y equals what? Y. So here now plus y cancels minus y. So here we'll be left with e to the power of e squared plus 1 equals y. Now let us flip this. It's still the same thing, but let's flip. Let's write it as y equals e to the power of e squared plus 1. So now what do we now do from here? Don't forget y, let us substitute back. Y is x to the power of x equals e to the power of e squared plus 1. Now, how do we solve this exponential equation is now the question. We have gotten rid of this and simplified. We got something like this. How do we solve this equation? Now, don't be deceived by the right-hand side. Everything here is a constant. E is a constant, E is a constant. This is just like saying x to the power of x, let's say equals 6, for example. This is a constant. So the question is now, when you have exponential equations like this, how do you solve it? Now, the most effective way you can solve this is by using the Lambert omega function. Yes, the Lambert omega function that we got rid of here, we have to make use of it here again to solve this exponential equation because logarithm can't help us. If we take log of both sides, we can't solve it directly, right? Algebra can't help us. So the best thing to do is use Lambert omega function. Now, how do we use Lambert omega function here? So in case you don't know Lambert omega function very well, don't be confused. By definition also, if we're to use Lambert omega function to solve this question, what we should do is that we should make this variable have the form of y e to the power of y. That's it. So Lambert omega function tells us that for you to be able to use me, what you should do is that your letters, that's your variable, make sure you express it in the form of that letter e to the power of that letter. Once you can express it this way, then I can help you, right? That's what Lambert is telling us. Now let us try to express this in this form. Now Lambert has left us. We are left to use our algebraic and our logarithm idea to convert this to this. So how do we do that? First of all, let us take lane of both sides, right? Let's take lane of both sides. We don't like this power. Let's bring it down. So when you take lane of both sides, you have x lane x. That will be equals to e squared plus 1 lane E. Yes, that's very nice. E squared plus 1 lane E. Now, what do we do next from here? So we need x in this form and x as a power. What should we do? Now, we have to use our idea of the law of logarithm. Now, logarithm tells us that you can just have any letter like this, like our x now, you can have any letter, right? And express it in form of a power on its own. What it means is that you can have this y can be expressed in form of a raised to the power log y base a. Yes, whenever we have a base that is a and this a base of a logarithm, the same letter, right? You can just cancel out like this and we have y. So we can express y, that's an isolated letter in form of logarithm like this, right? That's a beautiful law. So we can use that here, right? So it means we can express x as e to the power of lane x, then times this lane x. We haven't done anything wrong because lane is logarithm to the base of e. So we have that's e to the power of log x base e. Can you see log e cancels e? We have x. That's mathematical genius. Let's continue. Then equals to e squared plus 1 because lane e gives us 1. That law of logarithm log a base a gives us 1. Lane e is log e base e. So it gives us 1. So it has gone. Now, you can say that we have brilliantly done what Lambert said we should because here now we have a form of x as a coefficient and also that same form as a power. Let's rewrite this as lane x times e to the power of lane x equals e squared plus 1. Can you see? That's brilliant. Now we can now call Mr. Lambert to come and assist us here because we have done what he said we should. Yes, we have expressed this here in form of this. Now let's call him Lambert. Come and help us. Now Lambert now tells us that, oh yeah, you have done it this way. So to get this, the answer of this will now be the w function of the constant you have by the right. It tells us that this your variable, just pick one, any of these, just pick one, so they're the same. This variable here will be equals to the w function of the constant you have by the right. E squared plus 1 is a constant. E is also a number, right? So they are all constants. So this is how Lambert omega function can actually help us. So it means that now we can now solve for x directly like this. Yes, we can solve for x directly because lane e is log x base e. So here we can now have x equals to e to the power of Lambert function of e squared plus 1. Final answer. Yes, this is our final answer, but we can go further if we want approximation because everything here is a constant, right? Using our scientific calculator to give us the answer. When we input everything here into our scientific calculator, then x will be approximately equals to 5.13037, right? So this w, you can find it as product log in your calculator. So that's our final answer. Very, very simple. So you can see that this scary looking equation has been reduced to this as simple as ABC. Please, if you know that you enjoyed this and you learned something, please subscribe to my channel to learn a lot more like this and to be better at maths. Till next time, bye bye.